In this section, obviously, since last time we did multiplication of polynomials, this time we're going to do division of them. And I'm going to make use of one rule, and I'm going to make use of it over and over and over again, and that's this one. If I have a sum in the numerator of a fraction, then I can break this up into a sum of fractions. And so that's the one thing that I'm going to use besides the quotient rule. And I don't really have to explain anything as far as new material. All I have to do is some examples to show you what we're talking about. So let me start it off with the following example. I have 4a to the fifth minus 10a to the fourth plus 6a cubed, and all of that is over 2a to the third power. So now I'm going to go ahead and break these up. So I have 4a to the fifth over 2a cubed minus, where am I getting the minus from? Well, it's right there. Then I have 10a to the fourth all over 2a to the third. And then I have 6a to the third over 2a to the third. So now I'm going to simplify each and every one of these pieces. And when I'm done with that, the problem is finished. So what do I mean? Let's start with the first fraction right here. Notice that 2 goes into 4 twice. So I've got that. And notice the a cubed is less than a, the 3 is less than a 5 here. So I can cancel out the cubed, but I need to subtract a 3 from that particular a. So for the first piece, I just have 2a squared. 5 minus 3 gave me the 2. For the next one, 2 goes into 10 5 times, and then a to the third goes completely into a to the fourth. I can subtract the 3 from that exponent, and that one there gives me just 5a to the 1. I won't write the 1. Then on the last one, 2 goes into 6 3 times, and notice that the a cubes completely cancel this time, and all that I'm left with there is a 3. So nothing new here. It's just a matter of reformulating things we've already done. So that's the gist of this section. This is all I'm going to be doing, are problems of this nature. For my next one, I have negative 15 m to the sixth plus 10 m to the fifth plus 20 m to the fourth minus 35 m cubed. And all of this is over 5m cubed. So let me go ahead and break this up, seeing as I think I'll need a lot of space for this one. I'm going to start all the way at the left. So I got negative 15 m to the sixth over 5m cubed. Then I have plus 10 m to the fifth over 5m cubed. Then I have 20 m to the fourth over 5m cubed. And then finally, negative 35 m cubed divided by 5m cubed. And let's see what happens in each case. For the first part, I know I'm going to have a minus, so I'll put it down. 5 goes into 15 3 times, and m cubed goes completely into the m to the sixth, so I'll subtract the exponent. So for this piece, I have negative 3m cubed. Then for my next one, 5 goes into 10 twice. M cubed gets divided into the m to the fifth, so I subtract that off, and I end up with 2m squared. Moving on to the next one, 5 goes into 24 times. M cubed, I can subtract a 3 off of that 4 in the exponent, and I get plus 4m to the first power, which is just m. M cubes, they cancel in the last piece. 5 goes into 35 7 times, so I'm just left with minus 7 for that particular part. Next one is just a different view on division. So I got negative 32 q to the 6th minus 8 q to the 3rd plus 4q squared. That quantity is divided by negative 4q squared. So this is no different than the previous problems. It just looks different because of the way it was set up. Let me rewrite it so it looks exactly like the problems we were doing. And there we have it. Now let me go ahead and break it up. So I have a negative 32q to the 6th divided by negative 4q squared minus 8q to the 3rd divided by negative 4q squared, and then plus 4q squared divided by negative 4q squared. And so let's go ahead and simplify what I can. Notice that these negatives cancel in the first one. 4 goes into 32 8 times, and q squared can go into q to the 6th, so I'll subtract a 2 off of that exponent. So I get 8q to the 4th for that piece. Next, those negatives cancel again. 4 goes into 8 twice. Q squared will go into q to the 3rd, so I'll write that as q to the 3 minus 2, or q to the 1. You don't have to write the 1, so I don't know why I did. I normally do not. For the last one, it's negative, but everything else cancels out, so it just leaves a 1. For our next one, we have negative 54 j to the 5th plus 30 j to the 3rd minus 9j squared plus 15, and all of this is over 9j. Remember 9j, that j is to the first power. So let me break it up. I get negative 54j to the 5th divided by 9j plus 30j to the 3rd divided by 9j minus 9j squared divided by 9j plus 15 divided by 9j. And let me simplify what I can. For the first fraction, I got a minus. 9 goes into 54 6 times. And then j I can take out by subtracting 1 from the exponent in the numerator. So I get 6j to the 4th for that piece. Moving on, 9 does not go into 30, but I can cancel out a 3 and leave a 10 and a 3 in their place. Once again, j to the 1 will go into j cubed, so that'll end up being a 3 minus 1 on that exponent. And I'm left with 10j squared over 3. I can't clean that one up any more than that. I have a minus for my next piece. 9 goes into 9 all the way. J goes into j squared. And so that leaves just a j. And for the last one, all I can really do here is cancel out a 3, and I'll get 5 over 3j. And that's as far as you can go with that. For those whose instructors care about this stuff, not that big of a deal to me, since we're not going to do much with this kind of division. But this stuff here, all of this stuff before the fraction with the j in the denominator, this stuff, all of it in front of it, is called the quotient. And then you have the fractional part. For my next one, let's see, we have 60z to the 5th plus 3z to the 4th minus 10z divided by 5z squared. And once again, I'll write this like our other fractions so that it looks like it. And then I'll break this up. 60z to the 5th over 5z squared plus 3z to the 4th over 5z squared minus 10z divided by 5z squared. And so for this one, 5 goes into 60 12 times, and the z squared can go into the z to the 5th. So for that particular piece, I'll have 12z cubed. Now for my next one, 5 and 3, I can't do anything about those, but z squared can go into z to the 4th by subtracting that exponent. So I'll be left with 3z squared divided by 5. And then for the last piece, 5 goes into 10 twice. This time the exponent on the z is bigger in the denominator, so I can cancel the top z into the bottom one by subtracting down there from the exponent. So I have 2 over z to the 1 power, or just 2 over z. So when you do your subtraction of exponents, the one that wins is the one that's bigger, basically. Let me do another example. Oh, this one looks pretty complicated. Here we can do multivariable, which I think I haven't done one of these yet. So I have 24x to the 6th, y to the 6th, minus 54x to the 5th, y to the 4th, minus x cubed, y cubed, plus 12x cubed, y squared, and we're dividing this entire thing by 6x squared y. So I'll do like I did in all of the previous ones. I recommend, though, when you're doing this, look what I'm doing with my variables. I'm spacing them out because I know I'm going to start subtracting exponents. So I'm giving myself some room for that to happen. Numbers, they don't really need much space around them, but the variables, I think, do. And this is just a tip to help you out in doing these problems. All right, and let's see how much of a difference that made. The 6 goes into 24 4 times, so I've got that part. X squared can go into the x to the 6, so I can subtract 2 from there, leaving an x to the 4th. Y to the 1 will go into the y to the 6th by subtracting an exponent of 1. So we have y to the 5th power, and that takes care of the first piece. Now for the second piece, 6 goes into 54 9 times. So I brought down the minus. X squared will go into x to the 5th. I'll subtract that exponent, leaving x cubed. And then y can go into the y to the 4th, leaving y cubed. For the next one, I've got a minus, but there's nothing in the numerator for the 6 to cancel with, so it's going to stay around. The x squared cancels out completely with the x's, and the y, I can just subtract 1, leaving y squared. And because I don't need a vinculum that big, so I'll make it a little bit smaller, like so. And then finally, we've got a plus for the last one. 6 goes into 12 twice. X squared, I can subtract off of the x's, and then y I can subtract off of the y, and so we get 2xy. Oh, careful. I just noticed a mistake that I made. Up here, let me do it with my mouse pointer, x cubed. I wrote it down wrong. I had x squared there. X cubed goes there, and when I divided out the 2, so what that's actually going to do then is leave an x in that particular spot. I think the rest of it is good. For our next one, oh, this looks hideous. Let's see, we have negative 45 c to the 8th d to the 6th minus 15 c to the 6th d to the 5th plus 60 c cubed d to the 5th plus 30 c squared, no, I think c cubed d cubed. All of this stuff is divided by negative 15 c cubed d squared. And once again, I'll go through the effort of writing it like the other problems. Got to make sure that I get all my exponents correct. Oh, and like I said, well, I don't need to do it right now, but when I do break it up into pieces, I'll give myself a little space for when I go subtracting off exponents. So all of that is divided by negative 15 c cubed d squared. And let me break it up. All right, well, I said I was going to leave myself some space, and I actually did not. In the first fraction, these two negatives cancel away, so I can get rid of those. 15 goes into 45 3 times. C cubed goes into c to the 8th, so I'll subtract a 3 from that exponent, leaving a c to the 5th. Then the same thing is true of d. If I subtract 6 minus 2 is 4, so I get d to the 4th. The next one, these two negatives will cancel, so we'll have a plus. 15 cancels itself away. C to the 3rd can be divided into c to the 6th, leaving me with c to the 3rd. And then we can do d, subtract 2 from that exponent, and that gives me c d to the 3rd. So I got c to the 3rd, d to the 3rd. And then the next one's minus. 15 goes into 64 times. The c cubes completely cancel. D squared goes into d to the 5th. And so I have 4 d to the 3rd. Yep, I think that's it. And then for the last one, I've got a minus again. 15 goes into 30 twice. C cubed cancels all the way. D squared goes into d to the 3rd, and we end up with 2d. For my next one, we have 9q squared plus 24q to the 4th plus 8 minus 6q minus 4q cubed all over 2q cubed. So I'll break this up like I normally do. I have 9q squared over 2q to the 3rd plus 24q to the 4th divided by 2q to the 3rd plus 8 over 2q to the 3rd minus 6q divided by 2q to the 3rd minus 4q to the 3rd divided by 2q to the 3rd. and we'll start canceling. So the very first piece, I noticed the q to the third, the higher power is in the denominator. So when I cancel, I'll subtract 2 off the exponent in the denominator, and that will leave me 9 over 2q. For my next one, 2 goes into 24 12 times. This time the higher exponent is in the numerator, so I'll subtract that way, and I'll get 12q. For the next one, not much here except that 2 goes into 8 4 times, and you get 4 divided by q to the third power. For the next one, 2 goes into 6 3 times. There's a minus. The smaller power is in the numerator, so I'll subtract from the denominator's power. And it looks like you get 3 divided by q squared. And then on the last piece, 2 goes into 4 twice, and the q to the thirds cancel completely, leaving me with just a 2. Let's see, then we have, perhaps this is an easy one in comparison to the previous ones, but it's a good chance for you to pause the video and see if you're understanding what I'm talking about. So for this one, there's not a lot of cancelings that go on, except x squared will go into x to the third, and for that piece you'll have 2 over x. For the next one, x does go into x cubed. Subtract 1 from that exponent and get 3 over x squared. And then finally 5 over x cubed. For that piece there was nothing to cancel. And then one last kind of problem that I happened to notice was in the textbook. Let me go and draw a picture of a rectangle, because it does involve that. So what you have is a rectangle, and you have its length, and the width is actually given as 6w. It doesn't matter if this follows anything realistic. All I care about are these dimensions. You're told the area equals the following: 9w cubed plus 6w squared minus 24w. And the directions are find L. That's what you're supposed to do. Now, the area equals length times width. So here's what we have. We know that that's L times 6w. My L is L and my width is 6w. But I'm also told that that area is equal to 9w cubed plus 6w squared minus 24w. So if I want to find out L, I have to take both sides of this equation and divide by 6w. So on the left, I'll get an L, and on the right, I'm going to break this up. 9w cubed over 6w plus 6w squared over 6w minus 24w over 6w. And now it's just like all the rest of our problems. The 6 goes into 9. Well, it doesn't really. 3 goes into both of those numbers, leaving a 3 and a 2. W does go into w squared, so w cubed I mean, so I'll get left with 3w squared divided by 2, plus, then for the last one, 6, the 6's cancel, the w goes into the w squared, so that will leave me with just a w, And then on the very last one, 6 goes into 24 4 times. The w's all cancel away, and we're left with just minus 4.